Okay, we're going to go over what the professor is calling flow of control. All it is deciding the logic of your program. What are the order of operations needed to accomplish my task? A slightly less linear way of looking at it. What is my decision tree? This can be like, am I out of food? So this can be our turning point of certain logic operations. Maybe we say no. And in this case, the result is do nothing. But if we answer yes, that's a different branch in the tree. We might ask another question. Do I want to cook? If the answer is yes, it's very simple. Buy groceries, and then finally cook and eat. In the no case, maybe it's more complicated. Can I afford restaurant? If yes, eat at restaurant. And if no, I think you get the picture, but if no, maybe we just buy a frozen meal. We have created a tree, a figurative tree. Really, any program you write is going to follow a similar decision-making pattern. Okay, so we have order of operations or decision tree as different ways of interpreting what control flow is. Another thing we could ask is, what are my priorities? How is my data shaped, and how can it change? This is obviously a more technical understanding, but like what I was calling state before, the state that I'm in, am I out of food, yes, no, the value of yes or no, true or false, is a piece of data. Once we've kind of thought about this, we might look to start implementing our code a certain way, and then another question becomes relevant. When it comes to actually implementing code, are there any conventions worth adhering to? Architecture would be things like, how are you defining the decisions and the states in your decision tree? Stylistic might be like, how are you breaking up your code into functions? Are you establishing naming conventions for certain values that you have? We'll get into that more. If that's a bit too vague, don't worry about it. There are going to be multiple different ways of doing things, and we ultimately get to choose what style and logic we want to build. And that is, of course, a blessing and a curse. This is VS Code. This is a code editor application. So in here you write code and you actually have an environment for executing that code built in, which is a super convenient way to develop. I think it's a pretty solid environment to work in. There will be a separate video that goes over how to set up a VS Code environment for C++. One of the first things you do when you're setting up your programming environment is you just test that very basic commands are working. And the convention for doing that is writing this Hello World application, where all it does is it prints something to your terminal. A terminal is an interface, a very basic interface for interacting with your code. For example, you might be prompted to input, how many eggs do you have in your basket? And you could write 12 and press enter, and then if your code is running and you have something set up to listen to that input, that 12 will be processed as a variable in your code. And then perhaps you want to output some processing that you've done to the number of eggs that you have and communicate that output back in the terminal. That is something you can do as well. Regarding output specifically, we have this tool called cout. Syntax is kind of weird, but STD stands for standard. The double colon is a way of saying referencing something inside this standard library. And then cout is a variable that is declared within that library called standard. Cout is our way of outputting to the terminal. If I just take my file, it's called test file, and I build it by pressing Command-Shift-B, and then I type ./testfile.cpp, this will execute my code. It actually might just be ./testfile. Let's try this. And there you go. Here we have hello world, and then this is just a new line if you were to press enter in a Google Doc or in any other kind of text editor. So we could change this if we wanted to. We could write whatever we want in here. If we rebuild, you'll see it has our new output. Something to note, this is some pretty odd syntax. You can imagine these as arrows that feed into this function. This syntax is very particular to standard cout and then its counterpart standard cin. You don't really see a lot of this double arrow sign elsewhere, but it's just kind of a C++ convention. We'll see enough of it that it shouldn't be that confusing with time. Anyways, a true-false value, I think you might remember from our last lesson, is called a Boolean, and it's named after this guy, George Boole. So this is a pretty common thing to write, is a chart showing that if you have A as a certain Boolean value and B as a second Boolean value, what does it look like when you combine them using the logical operators? So this double ampersand, this is saying combine A and B together, and if they are both true at the same time, then this expression itself is true. If either A or B is false, or both of them are false, we should evaluate this expression as false. If I have bread and I have deli meat, then I can make a sandwich. If I have bread and no deli meat, no sandwich. Deli meat, no bread, no sandwich. No deli meat, no bread, no sandwich! This is the OR operator. It's this double line. I think this line is also called a pipe. We might say if I have a board game or I have a video game, then we can have game night. If either of these are true, we satisfy the conditions for having a game night. But if neither one is true, then game night is not possible. Pretty basic. The last one is a NOT operator. This takes a value and negates a value. Unary just means requiring a single input. Technically, these are binary operators because they have two inputs. There's also such a thing as a ternary operator. We'll see that later. But anyways, this unary operator, the NOT operator, returns the opposite Boolean value to what you pass in. It's kind of a more finicky one because really it just depends on what you call your variable. Like, you could have a variable called isEnabled. You could just as easily call your variable isDisabled and then use the opposite logic to represent the story you want to tell. Using the NOT operator definitely comes up, but it's kind of this weird one where it actually depends on the way that you're representing your data. I'll quickly go over these relational operators as well. These are pretty straightforward. Just a small example of relational operators. We're taking a value of 2 and comparing it to a value of 3. We're saying if 2 is less than 3, execute this code. Otherwise, if 2 is equal to 3, execute this code. So this will not execute. Otherwise, execute this code, which represents when x is greater than y, because we know if x is not less than y and x is not equal to y, then it has to be greater than y. So if we run this with 2 and 3 as our values, you'll see we have the output x is less than y. Let's make x equal to y and rebuild. Now we get x equals y. And lastly, if x is equal to 4 and is now greater than y, we get x is greater than y printed out. So that's like actual code for you. Let's set x equal to 6 and y equal to 2, and then write out exactly the first one we're going to write is not x greater than 2. And something really cool is we can just pass in that value directly. Cout is going to take this value and print it in a readable format for us. Okay, so I've written out all of the different cases here. Before we actually break it down, let's just make sure our code is following the expected outputs. I'm just going to format this a little better. Okay, so you'll notice it just prints out 0 or 1 here. Let's break some of these down. Something I should quickly explain. When we wrap stuff in quotations here, this is writing what's called a string. And a string is just a series of characters. So when we write that sequence of characters, that gets outputted to our terminal. And so you can see I can write another string that breaks down our Boolean evaluation steps one step further. And obviously not true equates to false, which is that 0 we see. So if I rebuild and then I check my output, you can see now it includes this string, and then because we don't wrap this in quotation marks, this is interpreted as an actual numerical or logical expression. And so it's not going to print the sequence of characters, it's going to print whatever this evaluates as. In our case, it evaluates as 0. If we move on to the next one, is x greater than y? 6 is greater than 2, so true. And is y greater than 0? Y is greater than 0, so that's true. If we have two trues paired with an AND operation, then that should equate to true. And if we're unsure, we can just look at our table here. In fact, that is what we get. This last case is essentially saying, if either of these expressions evaluates to true, pardon my typo, then we should be equating the entire expression to true, and that is indeed what we see. Hopefully this all makes sense. I know this can be a lot of weird symbols to be seeing all at once. Just a friendly reminder, don't let syntax overwhelm you, because you will see this 1,000 times. Okay, we know how to evaluate booleans, but let's talk about actually doing shit. Let's spruce this up so it looks like a real-life example a bit more. Alright, we want to make an omelet, and that omelet requires, let's say in our case we want to make a 4-egg omelet, and let's say we have 10 eggs to work with. I've just named my variables accordingly, and here we have some code that tells us if we have enough eggs. I've also written a function up here that does something very simple. It takes the number of eggs needed and the number of eggs owned, and it returns the difference between the two to tell us what the number of eggs remaining we have after our omelet is cooked. So let's say we cook one omelet. At the end of that, we will have this number of eggs remaining, where this number is handled by our function that computes that. I'm actually going to change this. I'm going to just modify num eggs owned directly, so we are keeping things consistent. So we could write this code again and check, do we have enough eggs? At this point, we should have 6 eggs if we subtract the 4 from the first time we cook an omelet. So let's cook a second omelet. Now, if we check our eggs remaining, we won't have enough because we should have 2 left after cooking our second omelet, right? Let's run code and see that in action. Okay, we have a bug here. As you can see, eggs remaining after the first one was -6, and it turns out the bug is related to the math we do in compute eggs remaining. We should take the eggs owned and subtract the eggs required for that recipe. Let's follow consistent naming of our variables as we go here. So we have eggs required, eggs owned. We subtract the eggs required in that recipe from the eggs we own to compute the eggs remaining. That makes a lot more sense. Let's try again. That looks a lot more like what we need. So what would happen if we ran this again, printed out eggs remaining? We would run into negative eggs, which is an impossibility. But we're allowed to have a negative number, so if we want to realistically represent this process, there's some work to do. We shouldn't be allowed to cook another omelet after not having enough eggs to do so. So what can we do? We have this arbitrary number for the number of eggs required, and then this other arbitrary value for the number of eggs we own, but we don't really have a way of procedurally cooking omelets until we no longer can. This is where we get into the really useful, awesome world of looping. Looping is a way of running functionality over and over and over again until you reach a condition where you no longer should be taking the action that you are taking. How do we write this with C++? There are actually 2 ways we can go about it. For now, I'm going to show you the way that I think is a bit more readable. We're going to write what's called a while loop. You can see it follows a very similar syntax to what we saw with that if statement we wrote earlier, where we pass a boolean into a pair of parentheses. So when are we allowed to cook an omelet? We can cook an omelet when the number of eggs we own is greater than the number of eggs required, greater than or equal to the number of eggs required. Our current code doesn't change this condition at all. So what would happen is this would just run infinitely. I'll go ahead and show you that real quick. It's just printing out over and over and over again. Press Control C to stop that. So let's actually make sure that we modify the condition of our loop. We are taking this action to represent cooking an omelet. Let's just move it inside our while loop so that we continue to run this operation until we can no longer. I'm actually going to change the order in which stuff gets printed out here. So now we have a loop that runs until the number of eggs remaining is no longer sufficient. Things are working as expected, so great. There's 2 more statements to talk about. The first is called a switch case. I think the easiest way to understand a switch statement will just be by comparing what the difference in decision tree shape looks like with an if versus a switch. So with an if, it's very simple, like binary branch. You might end up with a tree like this, where you have a bunch of yes-no branches. If you want to make a decision tree where multiple branches are accessible from a single place, you would use what's called a switch statement. And if that made no sense, here's what I mean. With a switch statement, you get to choose any number of possible outcomes based on whatever you specify these cases to be. And this case can be any expression you want. So the use case I'm thinking of is going to involve a new variable type, and that type is called an enum. Enum is short for enumeration. So for us, like, we have this idea of a meal course, and it can only exist in one of these 5 values. Pretty similar to declaring an integer as equal to 1, you can declare a meal course as equal to one of these values. We're going to write things out using the full syntax just for clarity. But now what we can do, and AI is already auto-completing it for us, we can print out a different action to occur in any of our possible enumerated states. We run a switch on course. Course is our value that we defined here. Check course against all of these different cases that it can exist in. If course matches the state of being in bread, we will print out bread course selected. Let's rebuild our code and run it. That is exactly what happened. If we change this to appetizer and then we rebuild, you'll see now we have selected the appetizer course. Anytime you're dealing with multiple possible states at once, where you have a decision tree that can branch in more than just a binary yes-no way, a switch statement becomes very useful. The next and final thing we're going to look at is a for loop. So for is very similar to while. You can accomplish the exact same set of instructions with both of these commands, but they have different readability benefits for different use cases. It's useful to know about both and be able to use both. Depending on the use case at hand, you might select one of the two syntaxes to represent the way all of your logic is interacting. Before, when I was talking about what conventions do you want to follow, this is an example of one of those stylistic decisions that you can make. Okay, so how does the for loop work exactly? So the breakdown of a for loop is that it takes three sort of parameters, three commands that you pass in. The first one is an initialization. This sets up your loop to start at a specific state, and if that doesn't make sense, just bear with me. Then you specify a condition. So long as this condition is true, the body of your for loop will continue to execute. And finally, you have this incrementation. This could probably be more aptly described as state changer. This is your way of changing a value that might eventually set your condition to false, in which case your for loop no longer runs. We can run this code. Here you can see all the numbers from 0 through 9 are printed onto our console. Just as a note, we could take out this new line, and here's what that would look like. Also, just another quick note, this \n is exactly the same thing as standard end line. It's very much just a different strokes for different folks type deal. Both will accomplish printing out a new line. I think we should look at an array. And we've been going with food so far, so let's talk about a grocery list, for example. Here's the syntax for declaring an array of strings. First, we import the package that lets us use strings. A string is declared in the same exact namespace as the cout function we were seeing earlier. It's that standard name. The way to access that first item is by using that same bracket notation and then passing in the index of the first value. With programming, we always start with the 0th index. If we were to use 1, this would actually be the second item in the grocery list. Looking at the first item we index with 0, this should print out milk. And indeed it does. So how does this relate to a for loop? First, we have declared an array specifically of 3 items. You'll notice if I pass in 2 here and then include a third item, the compiler is going to get mad. We know that this is 2 values long, and so if we try to include a third here, we're breaking the rules. Let's go ahead and add a 4th value. Another thing we can do just to make our code a little cleaner, we can declare above the actual number of items that we expect here. And you'll notice actually we get another error. We have to tell the compiler this value is certainly not going to change, and so you can trust that by the time I pass it in as my array initializer, that array will be initialized to something consistent. And we do that by tagging const here. Const is short for constant, which means non-changing, immutable. Okay, all of that stuff out of the way, let's talk about the power of a for loop. So with a for loop, we can do something really cool where we can initialize an index. And this index is what we're going to use to access every value of our array here. What's our condition for running this for loop? We want to run this loop across every single item in our array. We can do that by checking, is our current index less than the number of items total we have in our array, which we've specified as 4. And then what do we want to do to index in order to access every item? We want to set it to +1 of whatever it was in the previous iteration. So we have all 3 of our parameters for our for loop. First is the initializer. We set an index to 0. Then we set the condition that specifies how long this for loop should run for. In our case, we tell it to run so long as our index is still able to access a value in our array. We update index to be +1 of what it was in the previous loop. For now, let's just print out every value in the list. We're saying item, and then we're going to print out the number, and then we're going to print out the array value at that index, using this bracket operator to point to whatever value the index currently is set to. If we build, and then we run this, we will see that we have printed out every single item in our array. Just to show you that you can accomplish the exact same thing with a while loop, here's the same exact functionality, but done using the syntax that is required for a while loop. We declare our integer. That's done in line in a for loop. We specify our run condition. That's done here in a for loop. Then finally, inside the body of the while loop is where we do our iteration or our state change operation. If I build and run this, you'll see first what our for loop has done, and then the exact same thing written as a while loop. So why use one over the other? If you do this 1,000 times, it becomes much more straightforward and much more readable to consider all of the operations for your looping conditions in a single line. Now that we have an understanding for some of these basic tools, I want to perplex you a bit just to get you thinking about some of the more interesting things that you can do. I'm going to do what's called a nested for loop. Nested in this case means I'm going to write a for loop inside of another for loop. What we put inside of this loop doesn't necessarily matter, but just so we have something appearing or executing every time this loop runs, I'm going to print out an underscore. Before we run the code, I'm going to quickly explain what's going on here. Our outer loop is going to run 10 times. And every time our outer loop runs, we are going to trigger an inner loop. 10 times in a row, we are going to trigger something else 20 times in a row, because we have set j to be less than 20 as our run condition. So what's going to happen is we're going to get 20 underscores that print in a row, and then we're going to get a new line printing, and then we're going to get 20 more, and then another new line, 20 more, another new line, 10 times, until I is finally equal to 10 and this code stops executing. When we run this code, you can see we have 10 rows and 20 columns of underscores. Pretty arbitrary example, but kinda cool. So remember how we could access the I value from inside this for loop? That actually means we can access the value from inside this entire closure. This is just one example, but I could change the run condition of my inner for loop based on the variable that gets iterated in the outer for loop. Here I'm just saying if the sum of j and I is less than 20, that is our stop condition. It might be an interesting exercise to try to consider what this output is going to look like. Let's walk through it for a second. We start with I equal to 0. When I is equal to 0, our loop looks like the same as if we added 0 here, right? J plus 0 is equal to j. So it's going to look like what it did before, a row of 20 underscores. Let's say we set I equal to 1 though. The next time our loop runs, I is going to be equal to 1. It's equivalent to saying check if j plus 1 is less than 20. If we consider the algebra here, this is the same as saying j is less than 19. In this case, we should get only 19 underscores. So if we do j plus I generally, what we're going to see is that the number of underscores is going to decrease with every row that we print out. The last row of underscores that we print out should be 10, because if we're writing j plus 10, that's the same as writing j is less than 10 in here, right? If we subtract 10 from both sides. So let's see how that looks. Let's see if our prediction is correct. And there you have it. When you look at this, it can be a bit confusing, but if you break it down, you can kind of figure out what your expected output should be step by step. That's going to do it for this video. Hopefully this didn't break your brain. For homework, I'm going to post a separate video. You should have VS Code set up and you should be able to run some code like this yourself. I might also assign some exercises for you to complete.